What's up? I'm Vin, and I'm going to go through the June 2026 Geometry Regents, and I'll leave a link to a copy of this Regents in the description below. Now let's get started. First up, we're doing the part 1 multiple choice. There's 24 questions here, and each one is worth 2 credits. Question 1, which transformation would result in the area of a rectangle's image being different from the area of its preimage? So the moment I hear that the shape's area is going to be different, I think of a dilation. So a reflection would not be the answer here, because if you reflect a shape over a line, the size of the shape does not change. So if I have a rectangle like this, and let's say this is my line of reflection, my new rectangle here is going to be the same exact size as the old one. So this one's out. A translation would not be the answer, because if I just take a rectangle like this and then I move it, so a translation 4 units to the right tells us to move it 4 units to the right, this new rectangle is the same as the old one. And then a rotation of 90 degrees counterclockwise tells us to just spin this thing around some central point here, in this case being the origin. So that also would not be the case. So right away, I know it's choice 4 just by process of elimination. But let's read this here. A vertical stretch of scale factor 3 with respect to y equals 0. So something like this, if I have a rectangle and it's somewhere on the xy axis, and I stretch it in the vertical direction with respect to y equals 0, that's just going to take the rectangle, let's say it looks something like this, and it's going to make it go up. It's going to make it taller, okay? It's going to increase the height by a scale factor of 3. And the other dimensions here going left and right are not going to change, but the vertical dimensions here, let's say I just triple the distance like this, this new rectangle here is definitely going to have a greater area than the original. So choice 4 is our answer. Question 2, in the diagram below of triangle ABC, points D and E are the midpoints of CA and CB respectively. Which statement must always be true? Okay, we're looking for the one that must always be true, not sometimes true. So if we transfer this information over to the diagram, we have point D is the midpoint of CA. So that means this segment and this segment are equal in length. And then we're told that E is the midpoint of CB. So we could say here that this segment is congruent to this segment over here. Okay, CE is congruent to BE. And we want to know which statement must always be true. So for this one, this is the mid-segment theorem. Anytime you connect two midpoints of two sides of a triangle, this piece over here we call the mid-segment. And it has some interesting properties. The mid-segment, every single time, is half the length of the third side and parallel. So here I could say that DE is parallel to AB, but I could also say that DE is equal to 1/2 the measure of AB. Okay, so choice 1 must always be true, and this is the mid-segment theorem. Question 3, in triangle RJM below, the measure of angle R equals 90 degrees, and MR is equal to 7.25 inches. If the measure of angle M is 35 degrees, what is the length of MJ to the nearest hundredth of an inch? So for this one, let's label this information here. They told us the measure of angle M is 35 degrees. I'm going to write this in, and our goal is to find the length of MJ, which is the hypotenuse of this right triangle. So here, let's think about what we know. We know the measure of angle M. This side over here is opposite. Okay, so this side here is opposite of angle M. And this one here, MR, is adjacent. Okay, so this one is adjacent to angle M. Now I'm writing this out, very detailed here, because when you're doing trig, you want to make sure you know which angle you're using in your trig function. So here I'm going to use angle M, so I have to label opposite adjacent according to where angle M is located, which it's located over here. So this side is next to angle M, and this side is opposite of angle M because it's across. Now, the side opposite of the 90-degree angle, we always call the hypotenuse. Okay, so that is not going to change, even if we're talking about angle J up here. But these are according to whatever angle you're going to use. So now let's think about this. So I hear the phrase here in my head. I'm like, okay, I know the adjacent side. So I know the adjacent side, and I want to know the hypotenuse. So when I hear adjacent hypotenuse, I think of cosine. And the way I'm able to say that is I think of the phrase SOHCAHTOA. So SOHCAHTOA helps us remember the formula for each trig function. And cosine, we would say, okay, cosine of any angle theta is equal to the ratio of the adjacent side over the hypotenuse. Okay, so that's what the letter arrangement means here. Like when we hear CAH in SOHCAHTOA, it means cosine of the angle is equal to the ratio of the side adjacent to the angle over the hypotenuse of the right triangle. So what I'm going to say here is cosine of the angle I'm using is 35 degrees. Okay, you're always using the positive acute angle inside the right triangle when you're doing questions like this, equals the ratio of the side adjacent is 7.25 inches over the hypotenuse. I could just put an X here, and that's what we're solving for. Now, this algebra sometimes could throw students off, but just know you can use a cool technique here. My coworker nicknamed this or gave this the name the swap. Okay, you could just swap the X and the cosine 35 and say X is equal to 7.25 over cosine of 35 degrees. Okay, and the rest I'll just type in the calculator. Now, if you get a calculator that has been reset, please make sure you go to mode and you switch from radians to degrees. And me personally, I like to go from auto to decimal because for a lot of questions, we need to write our answer in decimal form. So now I press second mode to go back to the main screen. And to make a fraction, I could press alpha y equals enter. If you have a new calculator, you could just press alpha x. And then we have 7.25. And we're dividing by cosine of 35 degrees. So cosine of 35, we press enter, and we should have 8.85. So once again, we're rounding to the nearest hundredth of an inch. So we're going to say here x equals, and we have 8.85. Remember, we look to the hundredths place. Here we have a 5. To the right is a 0, so we're rounding down to 8.85. Choice 3 is our answer. Question 4, a fish tank in the shape of a rectangular prism with a length of 35 centimeters, width of 17 centimeters, and a height of 25 centimeters is shown below. So here's the fish tank. If the fish tank is filled with water to a height 3 centimeters from the top, how many liters of water are in this tank to the nearest liter? And we have here 1 liter equals 1,000 cubic centimeters. So for this one, first we have to know the formula volume equals length times width times height. But for this question here, we have to be very, very, very careful. Please make sure that you include this detail, that the fish tank is filled with water to a height 3 centimeters from the top. So what this tells us, it tells us that the height of the water is not going all the way to the top. Okay, so the height is actually going to be 25 centimeters minus 3 centimeters because we're leaving space at the top so the water doesn't spill out. Okay, so the height would be 22 centimeters. Okay, so this is a very important detail. So first what we could do is we could find the volume of water. So we're going to do length times width times height, but we're going to use this height because we're talking about the volume of water. So now we have 35 centimeters is the length times the width is 17 centimeters and the height we're using is 22 centimeters. So now we could work this out. And then at the end, whatever volume we get here, we're just going to divide by 1,000. So we're doing 35 times 17 times 22. And this is the volume of water, but this is in cubic centimeters. So we would divide by 1,000 to convert units here. So we divide by 1,000, and this would tell us 13 liters. We're rounding to the nearest liter, so choice 2. Now, choice 2 is our answer, but I want to show a little bit more work so we could see how the units cancel. So the volume of water is 13,090 cubic centimeters because I'm doing centimeters times centimeters times centimeters, which makes centimeters to the third power. But this would be the volume of the water in cubic centimeters. If we want to talk about how many liters, we have to convert units here. So we would do 13,090 cubic centimeters, but we would multiply by this conversion factor. For every 1 liter of water, we have 1,000 cubic centimeters. Okay, so this would be the conversion factor we would use because these quantities are equal. So if I write them in a fraction like this, I'm really just multiplying this by 1. But we're going to express things differently here. The units cancel, so cubic centimeters cancel out. And when we divide, we get 13.09 liters. But to the nearest whole number, 13 liters. Choice 2 is our answer. Question 5, triangle ACE is drawn below. Triangle ACE is mapped onto triangle AXE after a reflection over side AE. Triangle AXE is then mapped onto triangle LXE after a reflection over side XE. Which side of triangle LXE is the image of AC? So for this question, there's a really nice shortcut that you could use. So what I like to think about is the order of the letters, because when they tell you one triangle is mapped onto another, they have to write the letters in corresponding order. So when they say triangle ACE is mapped onto triangle AXE, I just think, okay, ACE is going to triangle AXE. But then they tell us in the next part here that triangle AXE is then mapped onto triangle LXE. So then this is going to triangle LXE. And then they ask us which side here is the image of AC. Okay, which side of triangle LXE? Well, here's a nice little shortcut. AC shows up first and second. So that tells you that AC is going to get mapped to the first two letters of the next triangle are AX. And then the first two letters of the last triangle are LX. So that means that AC has to land wherever LX is. And choice 4 is our answer. But if you want to hit enlightenment here, we could draw this out so we could really see that choice 4 is our answer. But I really like using the corresponding sides idea, that the letters have to be written in corresponding order. So here, first, there's a reflection over side AE. So if I treat this one over here as a line of reflection, then I would just draw the mirror image of this triangle over that line. Okay, so you don't have to be 100% here. It's just to give you an idea of what's going on. So let's say this line over here, CE, would flip over here like this. And then this point over here, I'm going to connect over here like this. So this triangle now, I'm calling AXE. Okay, so this is AXE. And then the next triangle after this is the image of this triangle after a reflection over side XE. So that means I'm going to treat this line now as the new line of reflection. And then this triangle is going to flip over this one. So here, this point would go the same distance across, let's say to about here. So somewhere in this direction here. And then I would just connect. Okay, so this one would go here. And then this one would go something like this. It doesn't have to be perfect. It's just to give you an idea of what's going on. And the name of this new triangle is LXE. So this point I would have to call L. So now let's follow the progression of side AC. When AC reflects over this line, it's going to land over here at AX. And then when it reflects over the purple, it's going to flip over to this line here, which is at LX. So either way, choice 4 is our answer. Question 6, the lines whose equations are represented by y equals -1/2 x plus 2 and x plus 2y equals 8 are, and we have these answer choices: parallel, perpendicular, the same line, neither parallel nor perpendicular. So for this one here, the most useful formula we have is y equals mx plus b. So y equals mx plus b tells us the slope of a line, and that's the number in front of x. And it also tells us the y-intercept, so where the line crosses the y-axis. And we could find that by looking at the constant at the end. So the line that they started us with, this one here, we could identify the slope right away because it's in the form of y equals mx plus b. And we could say here our first slope is -1/2, and our first y-intercept is equal to 2. But the next line they gave us is not in y equals mx plus b form. So what we should do is we should solve this equation for y. So we could start by going minus x on both sides. So we subtract x on the left and right side. X minus x cancels, and then we have 2y equals, and on the right side, now we have -x, and we have a +8, but we actually have to write the +8 here, like this. So now with this step, to solve for y, just divide each term by 2. So we're dividing everything by 2. Now, if this part here isn't obvious, the -x/2, we could think of -x/2 as -1x/2, and this is the same thing as -1/2 times x. So I could say this line is now y equals -1/2 x plus 8 divided by 2 is 4. And then from here, we could identify the new slope, and the second slope here is equal to -1/2. That's the number in front of x. And then our new y-intercept is equal to 4. So what we have is we have two lines that have the same slope, and they have different y-intercepts. So this would tell us that the lines are parallel. Okay, so the lines have to be parallel. Choice 1 is our answer. One thing we could do to check our answer to be sure is we could graph both lines. So we have -1/2 x and then +2. And then the other line was -1/2 x plus 4. Okay, so -1/2 x plus 4. And for this one, I could also write a fraction. I could go alpha y equals enter. Or if you have a new calculator, you could just press alpha x. But this part here, it doesn't matter. The calculator will read this as -1 divided by 2 and then times x. But if you prefer to write it nice like this, you could absolutely do this. So -1/2 times x plus 4. And then I graph both of these. And notice that these lines here are, in fact, parallel. Okay, they have the same slope and a different y-intercept. So they are not going to intersect. If the two lines had the same y-intercept, then the answer would be choice 3, the same line, because they would overlap each other completely. But choice 1 is our answer. Question 7, right triangle ABC below has legs whose lengths are 6 and 8. What is the volume of the three-dimensional object formed by continuously rotating triangle ABC about side AB? So for this one here, first we have to know what it means to rotate a shape around a side. And in this case here, we are spinning around side AB. So if we spin this way, first we have to know that we would be looking at a cone. And I'm going to draw this off to the side here. So the cone would look something like this. So here's the cone, and not necessarily drawn to scale, but the cone would look something like this. If you want to see the original triangle inside here, this would correspond to point A. And then I'm just going to draw this down as nicely as possible. Point B would be right at the center of the circle at the bottom. And then point C would be off on the circumference of that circle at the bottom. So it would look something like this. Okay, let me just make this as neat as possible. Let's see here. So there it is. And then the units here, this side AB is 6 units long, BC is 8 units long, but now we'd have to say which part of the cone do these values represent. So the height of the cone is going from the point here at the top all the way to the center of the circle at the bottom. The height would be equal to 6, and the radius would go from the center to the circumference would be equal to 8. And then next, we could go to the reference page here and see that the volume of the cone is equal to 1/3 pi r squared times height. Okay, some of the formulas will say capital B times H, where capital B is the area of the base, but I'm going to point out here that the base area is going to be found by using the equation for the area of a circle, which is pi r squared. Okay, so this is the formula that we're going to need, and we just plug into it. So we're going to have volume equals 1/3 pi, and then we're doing radius is 8, and we're squaring it, times the height is 6. And now we just type this in. So we go back to the main screen here, and I could do 1/3. And then we have pi, but I don't have to write pi in. I could just add it at the end. So I have 1/3, and I'm multiplying by 8 to the second power. And then I'm multiplying by 6. And this tells me my coefficient of pi is 128, so choice 2. Now, a lot of students, what they'll do is they'll go, okay, 1/3 pi, and then they go radius squared. So they multiply by 8 squared. And then they multiply by the height, and they press enter, and they're like, oh no, my answer's not there. And that's because you're including the pi in the calculator part here. So when you're typing in, if this happens, you're like, oh no, my answer's not there. Well, then just divide by pi at the end, and it'll tell you the number in front of pi should be 128. So we have volume equals 128 times pi. Choice 2 is our answer. Question 8, in triangle ABC below, CE is the perpendicular bisector of AEB. Which statement is always true? So for this question here, there's a few ways we could do this. But one way is really knowing the definition of perpendicular bisector. So a perpendicular bisector cuts a line segment in half and makes a 90-degree angle. But a fancier definition says that every point on the perpendicular bisector is equidistant to the 2 points at the beginning and end of the line segment. So that would mean that AC and BC have to be congruent. And this would be true no matter which point I pick on this perpendicular bisector. Like, let's say I put another point up here and call this F. The distance from A to F has to be the same as the distance from B to F. Okay, and that's because, once again, every point on the perpendicular bisector is the same distance away from the 2 endpoints at the beginning and end of the line segment. But let's say we don't have that definition and we want to investigate a little bit more. Well, we could use the simpler definition, which just says, okay, a perpendicular bisector cuts a line segment in half and makes a 90-degree angle. But if this is true, notice that side CE is shared in both of these right triangles. So right now what we have is, we have triangle AEC is congruent to triangle BEC. And this is true by side angle side. Okay, so we showed here that we have 2 pairs of sides that are congruent in both triangles and this right angle between. So then why would AC be congruent to BC? Well, we could say CPCTC, which stands for constipated people can't take craps. No, it actually stands for corresponding parts of congruent triangles are congruent. So once we show these 2 triangles are congruent, then their corresponding sides have to be congruent. And this is as definitive as things get here, okay? When you show 2 triangles are congruent, then their corresponding sides and angles have to be the same. So choice 1 is our answer. Question 9, in right triangle ABC below, AB equals 9, BC equals 12, and altitude BD is drawn to hypotenuse AC. And we want to know which equation is always true for BD. So here they told us that ABC is a right triangle and the hypotenuse is AC, which tells us if this is the hypotenuse, then this angle here at the bottom is a right angle. But then they also told us that we have altitude BD drawn to the hypotenuse AC. So that tells us that we have two right angles over here like this. And anytime this happens, you're dealing with three similar triangles. And I know this because let's say I were to just put in some random angle here, a random positive acute angle of, let's say, 30 degrees. So if this angle here were 30 degrees, then this one would have to be 60 degrees to make 180 degrees. And if this one is 60, to make 90, this would have to be 30. And then if this is 30 and 90, this would have to be 60. And you see how all three of these right triangles, the small one, the medium, and the big right triangle, all have the same angles on the inside. So they are all similar. Okay, but the important thing here is noticing which angles are the same. So this angle here at A is going to be equal to angle DBC over here. So I'm just going to mark off the ones that are the same. And once again, I can say this angle and this angle are the same. And I could say that this angle over here is the same as this angle over here. And what makes this interesting is that we could use a trig ratio in any one of these right triangles, the small triangle, the medium, and the big right triangle. So let's start off here with choice 1, cosine of A. So if we look and remember the phrase SOHCAHTOA, cosine is the ratio of the adjacent side over the hypotenuse. So cosine A equals BD over 9. But the problem with that is if we use the first answer choice, that ratio, that's referring to this small triangle over here. And cosine of A would be equal to, let's see, well, adjacent would be side AD. So cosine of A would be AD over the hypotenuse of the small right triangle is actually this side over here where 9 is. But the problem is, notice it says BD over 9, and BD is not necessarily the same length as AD. So this one I can tell right away is not true. Okay, so this one is out. But now I go on to the next answer choice. And for the next one, we have sine of angle C. So sine of angle C, I could use two different right triangles. I could use the medium-sized one, or I could use the big right triangle. But if I use the medium-sized one, so that's this right triangle over here, and let's switch colors so this stands out. So this right triangle here. If I apply the sine function here at C, well, opposite of C, since sine is going to be over here, we could look, sine is opposite over hypotenuse. Opposite of angle C is side BD. Okay, so BD is the side opposite. And then over the hypotenuse of this right triangle in red is across from this right angle, and the hypotenuse would be 12. So right away, choice 2 is good. But let's see, why are the other answer choices no good? So another detail we could go with here is that this side is 9 units long and this one is 12 units long. And if I draw out a 3, 4, 5 right triangle, this is a popular right triangle that shows up a lot. This right triangle ABC is similar to this one. I would just have to use a scale factor of 3. 3 times 3 is 9. 4 times 3 is 12. So AC, I could use Pythagorean theorem or just use similar triangles and say 5 times 3 is 15. So why is choice 3 no good? Well, if I look at tangent of A, opposite of A, because tangent is opposite over adjacent, opposite is BD. So let me just clean that up, is BD. But then over AD. See, AD is the side adjacent to A in the small right triangle. But the problem is, if 9 is the hypotenuse of the small right triangle, AD cannot be equal to 9 because the hypotenuse has to be the longest side. So this one here right away is not true. And then the last one here, sine of C equals BD over 15. Well, this one's incorrect because 15 is the hypotenuse of the big right triangle, not this medium-sized one. So that's why choice 4 is out. Definitely choice 2. Question 10, which regular polygon, when rotated about its center, carries onto itself after both a 120-degree rotation and a 180-degree rotation? So for this question here, it really helps to know 360 divided by n, which tells you the minimum degrees of rotation that you have to rotate a regular polygon about its center so it maps onto itself. And let's say I just run through the answer choices here. So for a triangle, n is equal to 3. So I would do 360 divided by 3 equals 120. And what this tells you is if we rotate an equilateral triangle, because a regular polygon just means all sides, all angles are the same. So for a triangle, that would be an equilateral triangle. And if we rotate an equilateral triangle 120 degrees, or if I do 120 plus 120 is 240, I get 240 degrees. And then another 120 would be 360 degrees. But if I rotate an equilateral triangle this many degrees about its center, it will map onto itself. So this answer choice is no good because it would have to work for 120 and 180. Now, just so you could see this concept a little bit more, I'm going to get a rough sketch here of an equilateral triangle off to the side. So if we have an equilateral triangle, and I'm also going to throw it inside of a circle. So let me draw a circle as well. So we have a circle like this. And you know what? I'll draw the triangle now that I have the circle and an equilateral triangle inside. I want you to see how this minimum degree of rotation stuff works. So here's the equilateral triangle and it's inscribed here inside, the circle. And if I rotate the shape here 120 degrees about its center, well, what I like to imagine here is if I connect all 3 points of the triangle or all 3 vertices of the triangle to the center like this, notice that it breaks the circle up into 360 divided by 3 or 120 degree angles. So when I rotate 120 degrees about the center here, notice that if I go this way clockwise, this point would go here. And if I go another 120, it would send this top point over here. And if I go 360, it would be right back to where it started here. So you could do this for all of the shapes here, or you could just remember the formula and then just trust the process here. You do 360 divided by n, and then you just list the multiples of that number. So if I did a square next, I would do 360 divided by 4 is 90. And then if I start counting by 90s, I get 90, 180, and then I get 270, and I get 360. So a square would work for a 180 degree rotation, but it wouldn't work for a 120 degree rotation. See, between 90 and 180, 120 is in between that. So this one here would not work. Now, one other thing I want to mention about the equilateral triangle. If I were to take an equilateral triangle, let's say this one here like this, and I rotated 180 degrees about the center, it would flip upside down like this. So that's why this would not map onto itself. We could see like this, that it would, make this star-like pattern here. So that one here would be no good. And now on to the next choice here, a hexagon. A hexagon actually works because when I do 360 divided by, for a hexagon, the number of sides here is 6. I get 60. And if I count by 60, I get 60 degrees. 60 plus 60 is 120, plus another 60 is 180, and then 240 and so on. But notice that it has 120 and 180. So this one here is our answer. Octagon is no good because if I do 360 divided by 8, that's 45. And when I count by 45s, I get 45, then I get 90, then I get 135, and then I get 180. So 180 is in the list, but 120 is missed. So 4 is out, definitely choice 3. Question 11, the coordinates of the endpoints of PA are P 3, -6 and A, -2, 9. If point C is on PA, what are the coordinates of C such that the ratio of PC to CA equals 1 to 4? So for this question, you could just memorize this formula here. Let's say X equals X1 plus, and then we have P over P plus Q times X2 minus X1. Now, I'll explain what all of these terms mean here. X1, Y1 refers to the first point that you're given here. So we have X1, Y1, and then we have X2, Y2. And with a directed line segment question like this, because that's what's going on here, it's a directed line segment, we want to say here, point C is on PA, and we want to know what are the coordinates of C if the ratio of PC to CA is 1 to 4. So in the ratio here, the first part is the value P, and the second part here is the value Q. So I'll just show how to use this formula, and then I'll show how to use the graph so you could see the concept. So we'd have X equals, and then we have X1 is 3, plus P is equal to 1 over 1 plus 4, because I'm doing P plus Q. And then X2 minus X1, I'm doing -2 minus 3. So now I work this out. I have X equals 3 plus 1 over 5 times -2 minus 3 is -5. And now over here, -5 over 5 simplifies to -1. So this would make X equals 3 minus 1. So X equals 2. And for this one, notice the only answer choice that has an X value of 2 is choice 4. But the other way to do this, and I like this way because it really does highlight the concept, is to draw this out. So P is at 3, -6. So that's over 1, 2, 3, and down 1, 2, 3, 4, 5, 6. So here's point P. And then point A is at -2, 9. So that's to the left 2, and then up 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's over here, over in this location here. And point C is going to be on this line segment. But now we really have to understand what that ratio means, breaking something into a ratio of 1 to 4. Well, if your ratio is 1 to 4, that is 5 equal parts. Okay, so 5 equal parts. So the goal is to break this line segment into 5 equal parts. So what I like to think of is the rise over the run. So if I'm going from point P to A, I have to go up. Well, I could cheat a little bit here. The way that I cheat through this is I'm going from a height of -6. So I'm down here at -6, and I'm going up to 9. So I know I have to go up 6 and then up 9. And if I do 9 plus 6, that's equal to 15. So I have to go up 15. So I'm going up 15. And then I'm going to the left. So I go up 15 and then I go to the left 1, 2, 3, 4, 5. But if I have 5 equal parts, I'm going to divide each of these by 5. And that tells me I could also go up 3 and to the left 1. And watch what happens when I do that. So I go up 1, 2, 3 to the left 1. Up 1, 2, 3 to the left 1. Up 1, 2, 3 to the left 1. And then up 1, 2, 3 to the left 1. And we want to know the location of C such that the ratio of PC to CA is 1 to 4. So that would tell us that point C has to be over here. Okay, point C has to be in this location. Because notice that PC here, I have 1 equal part. And then I have 1, 2, 3, 4 equal parts after it. Okay, so C would have to be over here at the point 2, -3. So choice 4 is definitely correct. Question 12, on the set of axes below, triangle blue is the image of triangle red after a dilation. What are the scale factor and coordinates of the center of dilation of this transformation? Well, for one, we could find the center of dilation first. And the way that we do this is we draw a line that connects the corresponding points. So B and R would be corresponding here in these two triangles. So I'm just going to draw really I could just draw a line segment here. I don't have to draw this forever. And I'm going to connect B to R and go all the way through. Now, the next pair of points that correspond, I could say, are L and E. So I connect L and E and I draw my line segment all the way through like this. Okay, so I'm going to connect all the way through. And right away, it looks like our center of dilation here is at the point 1, 0. So you look over here, it looks like this is happening at 1, 0. So choices 1 and 3 are out. And just know, if I did the same thing here for the last pair of corresponding points, so U and D, then if I do this, it should also go through that center of dilation. And notice here that it does. Okay, so, but I only have to do it twice here because all 3 will meet at the same place. But now let's follow this center of dilation. So let's say I call this point over here. Let's see, they didn't use the letter W, so I'm going to call this the letter, actually I could use the letter C for center. Okay, so I'm going to call this point C. To get from C to E, see how, like for me to get from C to E, I have to go up 1 to the left 1, 2, 3. So I'm going up 1 and then I'm going to the left 3 units. But then let's think about, how do I get from C to L? To get from C to L, I have to go a greater distance. I have to go up 1, 2, 3. So I'm going up 3 and I'm going to the left. From here, I'm going 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so here it looks like, see how my scale factor here would be equal to 3, because instead of going up 1, I'm going up 3 from the center. And instead of going left 3 from the center, I'm going left 9. Okay, so that would be a scale factor 3, not a scale factor 2. So this one here is out and it's definitely choice 4. Now, another thing I could do here is I could just do the same distance all the way through. See how I have to go up 1 to the left 1, 2, 3. If I go up 1 to the left 1, 2, 3, that puts me over here. And then I do it again, it puts me here. And you could see that CE compared to CL, CL is definitely 3 times as long. So that's why choice 4. Question 13, what are the coordinates of the center and the length of the radius of the circle whose equation is x squared plus y squared equals 45 plus 4x? Okay, so for this question, a few things we have to know. One is the equation of a circle. X minus h squared plus y minus k squared equals r squared. And when our equation is in this form here, we could identify the center. The center is located at the point h comma k, and the radius in this equation here is equal to r. So first we have to know this formula and know what each piece of the formula means. And then we have to know how to get the equation in that form. Okay, so let's go ahead now and do the algebra. So we have x squared plus y squared equals 45 plus 4x. Now, the algebra for this is a bit tricky. To do the algebra here, we have to know how to complete the square. So from here, what we could do is we could subtract 4x on both sides. Because when I complete the square, I like to have my x squared and x term together, my y squared and y term together, and the constant on the other side. So we subtract 4x first. And now I'm going to write this a little bit different. I'm going to write x squared minus 4x, but then I'm going to leave a space. And then I'm going to say plus y squared. And now equals, I have 45 on the right side. Now, when you are completing the square, the idea is you want to look at the b value. And when I say b value, I'm referring to back in Algebra 1, when you had y equals ax squared plus bx plus c. The b value refers to the coefficient of x. And here we have a b value of -4. We want to take the b value divided by 2 and then square it. And this would give us -2 squared, which is +4. And whatever number you get, that's the number you add to both sides so that you actually complete the square. What completing the square actually means is turning the quadratic into a perfect square trinomial. Okay, so this quadratic piece over here is now a perfect square trinomial when I have to come up with two numbers that have a sum of -4 and a product of 4. Those numbers would be -2 and -2. So I would say x minus 2 times x minus 2 like this. And then I could say plus y squared equals 45 plus 4 is 49. Once again, why they call this a perfect square trinomial, this part here, this trinomial is expressed as the product of two matching factors. Think of a number like, let's say 49 is 7 times 7. 49 is a perfect square because it could be represented as the product of two identical factors here. So that's why we call these perfect square trinomials. So now I just simplify. X minus 2 times x minus 2 is x minus 2 squared, plus y squared is maybe a little tricky to see how it goes into this form here. I could call this y minus 0 squared if I want. This is equivalent to y squared. Or I could just leave it as y squared, and this is equal to 49. But maybe why this could be more helpful is now we could identify the center. So the center is hk, and we can see our h value here. Don't say -2. The h value is going to be the opposite here, is going to be +2. So we have a center at +2, 0. All right, and I know it's 2, 0 because y minus k, our k value here is equal to 0. So we have a center at, let's see, 2, 0. So right away now we could eliminate these two answer choices. And then the radius here, be careful, is not 49. The equation says that the number on the right is r squared. So r squared equals 49. So if I take the square root of this, r is equal to 7. Okay, so choice 1 would be our answer. Question 14, in right triangle EFG below, altitude ET is drawn to hypotenuse FG. And over here we have if EF is equal to 17 and FT is equal to 15, what is the length of TG to the nearest tenth? So for this question, the first thing I would do is label. EF is equal to 17, so I put a 17 here. FT is equal to 15, and we want to know what is the length of TG. So for this question, the quickest way to get to the answer is to use the leg rule. Okay, so the leg rule says that when we have, let's say over here, we have hypotenuse over leg 1, that's going to be equal to leg 1 over part 1. And I'll label this triangle here so we see what each piece means. So the hypotenuse refers to, in this case, FG. This is referring to the big right triangle. And just know the leg rule and altitude rule only activate when you have a right triangle to start, which we know we have because they told us in the beginning, and they drop an altitude down from the right angle to the hypotenuse. Then you could use altitude rule and leg rule. You can't use it whenever you want, but in this case, we can use both of them. So here, the hypotenuse refers to side FG. Okay, so this entire space over here. So from here, just make that neat. So from here all the way to the end, that's the hypotenuse. And then this I could call leg 1. This is one of the other sides of the big right triangle. Part 1 refers to, I think of it almost as like the shadow of leg 1, okay, dropping down here like this. But this would be part 1, this would be part 2, and this would be leg 2. This piece here I would call the altitude, all right? But I'm just going to abbreviate it like this. So the leg rule, I could use this formula, but what makes it maybe a little bit tricky here is the hypotenuse is broken into pieces. It's 15 in x, So the hypotenuse would actually be 15 plus x. Leg 1 would be equal to 17. And now I set this equal to leg 1 is 17 over part 1 is 15. And now from here, I just cross multiply. So I do 15 times 15 is 225 plus 15 times x is 15x. And now equals 17 times 17 is 289. So now we can work out the rest. We subtract 225 on both sides. And on the left side, 225 minus 225 cancels. And we get 15x equals the difference of these two numbers. I could work this out in the calculator or just do this myself. 9 minus 5 is 4. 8 minus 2 is 6. 2 minus 2 just goes away. So we have 15x equals 64. And now we just divide both sides by 15. So we can work this out. 64 divided by 15 gives us this value here. To the nearest tenth, I just look at the tenths place as a 2. To the right is a 6. So I round up to 4.3. So we have x is equal to 4.3, which tells us choice 2 is our answer. But let's say you, like everybody else, skips leg day and you forget the leg rule. Well, another way to do this would be to use the altitude rule. Okay, so for the altitude rule, what you do is you could do part 1 over the altitude equals the altitude over part 2. Okay, so we could use this. There's another cool idea that gets mixed in with this. And we could say here that we have a Pythagorean triple. One of the popular Pythagorean triples is 8, 15, 17. There are some other ones. There's a less known one here, like 7, 24, 25. These are just popular right triangles that show up a lot in geometry and even in the SAT. So these are good ones to know, along with 3, 4, 5. There's also 5, 12, 13 is a popular Pythagorean triple. But in this case here, we have 8, 15, 17. Okay, so I see the 15 and 17 in the right angle, so I know the altitude is equal to 8. You could use Pythagorean theorem to get 8, but this is a nice little shortcut to have for a question like this. So now that I have that unknown side here, I could use the altitude rule, and I should get the same answer. So I have part 1 is 15 over the altitude 8 equals the altitude 8 over part 2 is x. And then I cross multiply, and notice I get 15x equals 64, and this gives me the exact same thing that we have over here. X is still equal to 4.3. Question 15, in trapezoid ERJT, sides ER and TJ are parallel. If the measure of angle R equals 2x plus 15 degrees, and the measure of angle J equals 3x minus 40 degrees, what is the measure of angle J? So for a question like this, please make sure that you draw this out, okay? Don't just try to do all of this in your head. That's a common way to get this question wrong. Just draw out any trapezoid, okay? It's really just to help you see which angles we are referring to. I mean, when in doubt in geometry, you either add the angles and make them 180 or you set them equal to each other. So if you have no idea what to do, I mean, I guess you could try that. But otherwise, what I'm doing is, okay, they told us sides ER and TJ are parallel. Now, a lot of students will struggle with something like this. They'll say, all right, ER, and then they'll write maybe like, all right, TJ like this. But this is no good because once you start labeling your diagram, it's very important that you go in the order of the letters. So if I put ER here, I'm committing to going in a clockwise direction like this. Okay, I'm labeling clockwise like this. And if I commit to clockwise starting here, then if E and R are in this location, then J would have to go here and T would have to go over here. So that's just so you make sure you are lining up the angles correctly. So that's very important. Remember, they told us ER and TJ have to be parallel, so I can't just label this any way I want. I have to make sure the parallel sides are like this. So now I could label the angles. They told us the measure of angle R is 2x plus 15 degrees, and they told us the measure of angle J is 3x minus 40 degrees. Now, it may not be familiar what to do here, but these angles are actually supplementary. Same side interior angles of a trapezoid are supplementary, and this has everything to do with the old math going back to the beginning of geometry. When you have parallel lines cut by a transversal, the corresponding angles are equal, but same side interior angles are supplementary. So I like to think of a trapezoid as just parallel lines cut by two transversals. Let's say something like this. The same side interior angles, whether you're on the left side or the right side, are going to be the same. This angle E is not necessarily equal to angle R unless this were isosceles, but these two same side interior angles are definitely supplementary. So what that means is we could add them and set the sum equal to 180. I could say 2x plus 15 plus 3x minus 40 equals 180. And now I just have to do the algebra. 2x plus 3x is 5x. 15 minus 40 makes minus 25 equals 180. Now I add 25 to both sides. So in the next step, we have minus 25 plus 25 canceling, and we have 5x equals, we're going to have 205. And now we divide both sides by 5, and we could say x is equal to, I do 20 divided by 5 is 4, and then 5 divided by 5 is 1. So x is equal to 41. Now, they were very polite to not put 41 there as an answer choice, because they're asking us here to solve for the measure of angle J. So we have to plug x back in for the measure of angle J. The measure of angle J is 3 times 41, and then minus 40, and this is all degrees. Okay, so here, this would work out to, you could just use a calculator for this part, but if I work this out, that's going to be 123 degrees minus 40 degrees, which works out to 83 degrees. Choice 3 is our answer. So for this question, I would just draw things out. And you have to know that in an isosceles right triangle, we have one right angle and two sides are equal. Okay, the legs are equal because this right triangle is isosceles. And they told us the hypotenuse is 14 units. So here, I could just use Pythagorean theorem. I could say that x squared plus x squared is equal to 14 squared. Okay, so for this one, we could just use Pythagorean theorem because we have all three sides. But even though two of them are unknown, we have the same value for both. So anytime you could create an equation where there's only one unknown variable, you could actually solve. So x squared plus x squared is going to give us 2x squared. And then 14 squared is equal to, we have 196. Okay, so that would be 14 squared. And then from here, I would divide both sides by 2. And then I would have x squared equals, if I divide by 2 here, that's going to give us 98 on the right side. And now I just take the square root of both sides and I could use the calculator. Now, of course, if I'm actually taking the Regents here or a test, mental math is fun, but I would double check the values that I just did here. So 14 squared definitely works out to 196. Then I divide both sides by 2. And then I take the square root of both sides to get x. And to take the square root, I press second x squared. And then I put 98 in. And this is going to work out to the nearest 10th. So I look at the 10th place is an 8. To the right is a 9. So I round to 9.9. So our answer to 16 is going to be choice 3. Question 17, in circle T below, tangent AS and secant ELS are drawn. And then we have if SL is equal to 8 and LE is equal to 10, the length of AS is, and we have these 4 options to choose from. So for this question here, it does help to know the circle rules. Now, there is a funny way to remember a few of the circle rules. You can remember the wee rule, okay? So the wee rule, how that works, so we say we equals we. And what this stands for, W represents the whole segment, and then E represents the part that is on the exterior, okay? Outside the circle. So exterior means outside, so outside the circle. So here I look and see, okay, 8 is an exterior piece. Okay, this is outside the circle. The whole segment though, ES would be the whole secant, is 18. I would just do 10 plus 8. So over here, I have the whole segment is equal to 10 plus 8, which is 18. So when I want to use this formula, I'm going to do, okay, the whole secant is 18 times the exterior piece is 8 units long. And now this is equal to, but with the tangent case, this is where things get a little tricky. So here, the whole segment is equal to x, and the piece outside, the exterior piece, is also equal to x. So this rule, the wee rule, is just, it's a funny way to remember all the circle rules. Otherwise, if you want a more formal formula, you could say that the tangent squared is equal to the secant. So the whole secant times the exterior piece. Okay, so maybe, you like this formula more, but the wee rule works if you have, 2 secants or even a tangent and a secant like we have here. So now I just work this out. So I have x times x is x squared. And then here I do 18 times 8. 18 times 8 makes 144. And then from here, all I have to do is take the square root of both sides. So then x is equal to 12 because 144 is a perfect square. 12 times 12 is 144. So the length of the tangent AS is choice 4, 12 units long. Question 18, parallelogram MERT has diagonals that intersect at I. Which additional statement is sufficient to prove MERT is a rhombus? So for this question, it's very important to understand what the actual goal is. We are starting with a parallelogram, and we want to know what information do we need to upgrade this parallelogram to a rhombus, okay? Or in this case here, the exact phrasing, which additional statement is sufficient to prove that MERT is a rhombus. So there's a few different ways you could upgrade from parallelogram to rhombus, and let's talk about those. So for a rhombus, one way to upgrade a parallelogram to a rhombus would be to show diagonals are perpendicular. Okay, so this is unique for a rhombus, that diagonals are perpendicular, and that would take your parallelogram and upgrade it to a rhombus. You could upgrade it more to, let's say, a square if you had more information, but the goal is to go from parallelogram to rhombus. So this is one way. Or we could show, all right, consecutive sides are congruent. Now, in a rhombus, all four sides are the same. So let me just draw a sketch here of a rhombus. So when I have a rhombus, let's say like this, all four sides are the same. So if I showed all four sides are the same, then I could just go right from quadrilateral to rhombus. It's like getting there really, really quickly. But I like to draw this out because if I forget any of these ideas, when I draw things out, it helps me remember the idea. So if I just draw in the diagonals like this, it wasn't my best drawing of a rhombus, but you could see the diagonals here are looking perpendicular. Now, they might not be perfect right angles. So maybe I start off here with, perpendicular diagonals like this, and then I could draw in my sides after. And I think we can see already this rhombus is already looking good. Now remember, a rhombus is a parallelogram, so the diagonals also have to bisect each other. So that could be another way to help you draw out a rhombus as nicely as possible. But now let's go ahead and label it. So they're calling this parallelogram MERT. So I like to start in this corner over here and then go clockwise. You could go counterclockwise. The only thing you can't do when you're labeling is you can't go ME and then TR. You have to commit to the order of the letters, whether you're going clockwise or counterclockwise. And the intersection is happening here at I. So now I just run through the answer choices. So choice 1, we have ERT. So that's this angle over here. So ERT, this angle is congruent to RTM. Well, let's think about what that's communicating. If these two angles here were the same, if consecutive angles of a parallelogram are congruent, that would make a rectangle, not necessarily a rhombus. Okay, you can even see the way I drew this. This angle looks acute, and this one here, actually this one looks acute, and this one looks a little bit obtuse. So I do not need consecutive angles to be the same to have a rhombus. So choice 1 is out. But this would show, if consecutive angles of a parallelogram were congruent, that would show that you have two 90-degree angles. And if you have two 90-degree angles inside a parallelogram, you automatically have a rectangle. So now let's look at choice 2. MEI, so this angle over here. So this one is congruent to RTI over here. Well, this would be true just for any parallelogram, because in a parallelogram, opposite sides are parallel. So then we have alternate interior angles formed here by parallel lines, which would make, congruent alternate interior. Well, let me start that sentence over. Parallel lines cut by a transversal, the alternate interior angles formed are congruent. So this would not upgrade to a rhombus. That would just be like, oh, cool, I have a parallelogram. Now I could say one more thing because I have a parallelogram. So 2 is nothing special for a rhombus. Now for choice 3, the measure of angle TIM equals 90 degrees. This is our answer. So you can see here, diagonals make 90-degree angles in a rhombus. So the measure of this angle here would have to be 90 degrees. So that tells us right away, choice 3 is our answer. Now, why is choice 4 no good? ME is congruent to RT. Well, this is true for any parallelogram. Opposite sides of a parallelogram are congruent. So that's nothing special. Yes, it's going to be true for a rhombus, but it's not enough to upgrade. So choice 4 is out. Definitely choice 3. Question 19, for the acute angles in right triangle ABC, sine of 3x degrees equals cosine of x plus 10 degrees. What is the measure of the smallest angle in triangle ABC? So for this question, there's a very important idea that we have to know. So let me just draw this a little bit nicer. But when we have a right triangle, let's say like this, and this one here, it doesn't have to be isosceles. It could be any right triangle. And let's say I go A, B, C like this. So the two acute angles inside of a right triangle, in this case we have A and B, the angles here are complementary, but sine and cosine are equal at those angles. And what I mean by that is I could say, based on this picture, that sine of A is equal to cosine of B. Okay, so this is for any right triangle, the acute angles. If you plug one of them into sine, then cosine of the other one is going to be equal to sine of the first acute angle. And the topic name is cofunctions. Okay, so that's if you want to review a lesson on why this works, the topic to look up is cofunctions. So sine and cosine are cofunctions. So sine of the first acute angle equals cosine of the second acute angle. And what we could assume here then, once we have this, if sine A equals cosine B inside a right triangle like this, then we can conclude that A plus B has to be equal to 90. So for these questions, I just take the first angle here, and I'll leave the degree part out. I'll just say 3x, but then plus the other one has to equal 90. Okay, so now I just solve this equation here. So we have this equation. I could say 4x plus 10 equals 90. And now we could go minus 10 on both sides. And we have 4x equals 80. Divide both sides by 4. And then x is equal to 20. But once we get x equals 20, we have to solve for both angles. So if I do 3 times 20, I'll do this over here. So 3 times 20 tells us that we have a 60-degree angle. So let's say this one over here is 60 degrees. And then this one would have to be 30 degrees to make 180. But if I want to double check, if I plug in x is 20 over here, 20 plus 10 makes 30. But they're asking us for the smallest angle inside the right triangle. So 30 degrees would have to be our answer because this one we have 30, 60, and 90. 30 degrees is definitely the smallest. Now, before we move on, just a little bit more about those cofunctions. I just want to show here that if I have two complementary angles, let's say 70 and 20, 70 plus 20 makes 90. But if I did sine of 70 and press enter, and then cosine of 20 and press enter, notice that I get the same values here. And this works. Let's say I have sine of 50. I know that 50 plus 40 makes 90. So if I throw 40 degrees into cosine, I get the same ratio. Okay, so just know, once again, when you have two positive acute angles that are complementary, sine of the first angle equals cosine of the second one. And that's the idea we're using for 19. Okay, next up, question 20. And question 20 I thought was the toughest multiple choice question on this Regents. And to be honest, one of the toughest multiple choice questions I've seen in a while, if you truly want to understand each answer choice. Okay, so here we have which two-dimensional shape below cannot be a plane section of a rectangular prism. So for this one, you need a bit of an imagination, but it also really helps if you could draw a rectangular prism. So I draw a rectangle like this, and then I draw some lines going back like this. So I'm going here, and then I draw a line coming down like this, and then I draw the dotted line coming down, and I try to make everything here as parallel as possible. Like I want this one to be parallel to this. I want this line going across to be parallel to the one in front. So a plane section, just imagine you have a blade of some kind and you are chopping this shape. Okay, so the blade, a plane section just means that it's going to be something like this. So just imagine here, I don't know, it's like a cleaver or something, like you're cutting vegetables, but you're just chopping this shape. Now you could cut it any direction you want. So a triangle is possible. So we want to know which one cannot happen. Okay, so a triangle is possible if you were to cut it in this corner here. So like, let's say I make a chop, coming down at an angle like this, and I chop the corner off, then I would be looking at a triangle. So a triangle is possible. So we are going to eliminate choice 1. Now the answer is going to be an octagon. And there's a nice way that we could reason this. A rectangular prism has 6 faces, okay? 6 faces. It has a top, a bottom, left, right, a front, and a back. And any way that we chop this, the sides have to go on one of the faces. Like you see the triangle we had before, it was on the top face, and then one of the edges went through like this towards the front face, and then the other edge of the triangle cross section went along the left side face. So in an octagon, there are 8 sides, but we only have 6 faces in this rectangular prism. So it just wouldn't be possible here to chop this anyway to show up with a 8-sided figure when we only have 6 faces. Okay, so that part I wouldn't say is the worst to understand. The hard part is like seeing the other shapes that are happening here. Okay, so this we could, just eliminate that answer choice. Now, I'm just going to draw over this. I'll just ignore this piece over here. Now, the pentagon I'm going to save for last because I really think that one is the toughest to see. But why is a trapezoid possible? Well, the new definition of trapezoid for the Regents is inclusive. And for a trapezoid has to have at least one pair of parallel sides. So technically, I could chop this right down the middle, and I would have a rectangle like this if I were to chop down the middle. Like, just imagine taking the knife and just like chopping straight down, straight through the middle, a vertical cut. You would have a rectangle like this. So that's one way of seeing like how a rectangle is possible. There are other ways that we could chop this to truly see a trapezoid, but that's the quickest way to argue why a trapezoid is possible. But why is a pentagon possible? Well, let's say I cut it at this angle here. So I'm going to cut it, let's say here, and then I'm slicing it. This is hard to explain and, with just a pen here, but I'm going to draw the points in first, and then maybe we'll be able to see like how this is possible. But let's say I chop this in such a way with the knife that it hits these parts here. So when I chop straight through, I'm coming at this angle such that it's going to hit here, and then it's going to come down and hit this. And then let me just draw this as nicely as possible. We hit here, here, and here like this. Okay. So if I were to chop, let's say this way through, like I cut it at a very awkward angle like this, it's possible that my knife goes through like this, and then I just follow along this plane like this, and then it's going to make contact with this part, then this part, and then this part probably last. And then if you could even do this, don't destroy all the butter in your house. That was probably the easiest thing to cut to see. But if you were to cut a small piece of butter as precisely as possible like this, of course, do this with adult supervision. I don't want people, oh no, like I cut my finger, maybe have a grown-up do it or something. Because I realize a lot of people here are, probably young. But in theory, if you did this, this is the shape that you would be looking at here. And a pentagon is possible. But trying to imagine the pentagon took a really long time to see how this was possible. But a pentagon is possible, so 3 is out. Definitely choice 2. Question 21, points A, B, and C are on circle D below such that DA equals 12, and the measure of angle ADB equals 150 degrees. The length of arc AB is, and we have these options to choose from. So for this question, when I want to find the length of an arc, what I would do is I would say, okay, the arc length. So the arc length is equal to, I take the circumference, and the formula for circumference is 2 pi r. But then I multiply it by theta, where this is the central angle. So the central angle divided by 360. Okay, so that's what I want to do here. And basically what you're doing is you're taking the whole circumference, but when you want to find the arc length, in this case AB, you're just taking a fraction of the circumference. And the fraction you take depends on the central angle. So I'm just going to plug this in. Arc length here, or in this case, I'm sorry, I'll just say it like this. I'll say the measure of arc AB since we're finding a specific one. So the measure of arc AB equals 2 times pi times the radius is 12. And I know this is the radius because circle D, the name of the circle tells you where the center is, and A is on the circle. So DA is a radius. So I have 2 pi times 12 times the central angle is 150 degrees, but I'll just say 150 over 360. I mean, if we want to write it with the units here, I could put degrees here and degrees here, and the units cancel. Or I could just say, all right, it's going to be 150 over 360. The units just cancel out. So we could sit here and do the math by hand, but this is much easier if we just type everything in. Now, the pi is attached to the answer. So when I multiply this stuff out in the calculator, I'm not including the pi. I'll just tag it, along at the end. So 2 times, I'm going to ignore the pi. So we have 2 times 12, and then times, not plus, so times 150 over 360. Okay, so we do this, and we get 10. So 10 pi is our answer. So once again, all of these numbers simplify to 10, but the pi is attached. So the measure of arc AB is 10 pi, choice 2. Question 22, the lengths of 2 sides of a triangle are 12 and 30. The length of the third side could be, and we have these 4 options to choose from. So the formula that we need for this question is the triangle inequality theorem, which says that the sum of 2 sides of a triangle always has to be greater than the third side. And the way I help students remember this or understand this formula is the phrase, the shortest distance between 2 points is a straight line. So you can see here, this straight line, let's say, is C units long. So the moment I leave the straight line, if I go A and then I go B, so I go A plus B, that's automatically going to take longer than just going the straight line. So that's why the triangle inequality theorem works in a simple explanation. But now you could just plug in all the numbers and see which ones work. So I know the third side can't be 12 because let's say here I just make space. So I have 12 and 30 at the end. If the missing side here were 12, well, 12 plus 12, the sum of the two smaller sides is not greater than the third. I would get 24 is greater than 30, and that's a false statement. So that's how I know choice 1 is no good. So now I try out a different side. So I have 18, but 18 doesn't work because then 18 plus 12, 18 plus 12, let me write this out, greater than 30 is also not true. 18 plus 12 is 30, and 30 greater than 30 is a false statement. Okay, 30 equals 30, so this one is no good. So 18 is not possible. 28, let's see how this one works. Well, for this one, if I did 28 plus 12 greater than 30, this one works because 40 is greater than 30. Okay, no matter which two sides I add together, they're always going to be greater than the third side. So this one here is possible. So once again, you could just have the formula and just plug in all the answer choices and hope for the best. The reason why 42 is no good though, is because if I had 12, 30, and 42, now 42 would be the greatest side if it were possible. And we would have 12 plus 30 greater than 42. And that is a false statement. 42 is not greater than itself. So that's why this one is not possible. Now, the other way to do this, which is a little bit more technical, is to start off by just drawing something out like this. And I don't have to draw this to scale, but let's say I have 12, 30, and x. Well, if I use the formula, there's two cases. This is either the biggest side or it's not the biggest side. If this is the greatest side, then 12 plus 30 has to be greater than x. Okay, if x is the greatest side. If x is not the greatest side, then 30 would have to be the biggest side. So I would have another inequality that I could set up here. So this way is more technical, but it's like pretty definitive and it gets you right to the answer. So option 2 is, once again, x is not the greatest side. So then that would mean that 12 plus x has to be more than 30. So this gives me two statements. I have 42 is greater than x. And then if I subtract 12 on both sides, that tells me that x is greater than 18. But now I'm going to write this a little bit different. Instead of saying x is greater than 18, I'm going to say 18 is less than x. And instead of saying 42 is greater than x, I'm going to say x is less than 42. And now watch what happens when I squeeze these two statements together. So if 18 is less than x and x is less than 42, then x has to be between 18 and 42. And the only answer choice that is between 18 and 42 is choice 3. Question 23, in the diagram below, AC and ED intersect at B, and AE is parallel to CD. If AB equals 6, BC equals 2, CD equals 3, and BD is equal to 4, what is the perimeter of triangle ABE? So this is a similar triangles question. And the way that I know this is similar triangles is this part here, where they told us that AE is parallel to CD. Because once we know these line segments are parallel, then we could say E and D are congruent angles because of alternate interior angles. When you have alternate interior angles inside parallel lines, they are congruent. We also have vertical angles here. So now since we have two triangles that have the same angles, angle, in corresponding parts here, we could say that these two triangles are similar. Okay, so we have two similar triangles here. And our goal is to find the perimeter of the big triangle. But first, I would just label all this stuff. So we were told that AB is equal to 6. We were told that BC is equal to 2. And we're told CD is equal to 3. And BD is equal to 4. And we want to know what's the perimeter of the big triangle. Well, what's nice about perimeter is a one-dimensional measurement. Okay, so one-dimensional measurement, which tells us that we could just find the scale factor and then multiply the perimeter of the small triangle by that scale factor. But what we have to be able to say first is which side AB, like which side corresponds to AB in the small triangle. That could be a little bit tricky. So what I would do is I would label this third angle with 3, marks like this. So then angle C would have 3 marks as well. And notice that AB is between the 3 and the 2 marks. So the one between the 3 and the 2 marks is over here. So that's how I would be able to identify this. So I have triangle ABE. This triangle is similar to triangle And now I'm going to write these letters in corresponding order. See how A has 3 marks? Well, C has 3 marks in the small triangle. B has 2 marks, and B has 2 marks in the small triangle. E has 1 mark. See, it has 1 little mark here. So D would go last like this. So once again, when I'm identifying the corresponding side, AB is this one here, corresponds to CB. So CB here would be the one that's going to help us. So what that tells us is, okay, CB times the scale factor K has to give us the length of AB. So now I could just plug in CB is equal to 2. 2 times K is equal to AB is 6. And that would tell us that our scale factor is equal to 3. All right, so now what I could do is I could say, all right, the perimeter of, I'll just abbreviate, perimeter of the small triangle of triangle CBD. This I just add up. So I just have 2 plus 3 plus 4. And that's going to give us, we're going to have 5 plus 4 is 9. So then the perimeter of, so let me just make that neat. The perimeter of triangle ABE, I just take the old perimeter, 9, and I multiply by the scale factor of 3, which gives us 27, okay? I could find the length of the missing sides here. Like I could say, all right, 4 times 3 is 12, and I could say 3 times 3 is 9, and I could do 9 plus 12 is 21, and 21 plus 6 is 27. But this, is a nice way to get to the answer. Now, I just want to point out, if this phrase had changed to area instead, then this question becomes much trickier. You cannot just multiply by the scale factor. You'd actually have to multiply by the scale factor squared. Okay, so just be mindful of that. I was only able to do this, scale factor multiplying, trick because this perimeter is a one-dimensional measurement. The distance going around is one dimension. Question 24, on the coordinate plane, a line is dilated by a scale factor centered at a point on the line. The image of the line has, and we have these 4 options to choose from. Well, just know the concept, when you have a line, let's say like this, and your center of dilation is a point on the line. So that means, let's say we have a center like this. When you dilate a line and your center is on the line, well, what it would do is, let's say I have a scale factor of 2. It would take the distance from here to here and double it and push it out here. And let's say I had another point in this direction that I have scale factor 2, it would double the distance between the center and this point and push it out here. But notice that all of the points are still on the same line. So when you have a dilation of a line and the center of dilation is on the line does not change, okay? This is like one of those like very sneaky questions where it feels maybe a little awkward picking the answer. You're like, wait, the line doesn't change, but the slope and y-intercept are the same as the original line. So choice 1 would be our answer. The only time something a little bit more interesting happens is when your center of dilation is off the line. So let's say in this case here, I had my center off the line. Then when I do a dilation, and let's say I go scale factor 2 again. So scale factor 2, I would take the distance from, let me just draw this out, from here to here, and I would double it. So whatever that distance is, I would just go the same amount out. And then whatever the distance is from here to here, I would just go the same amount out like this. And then watch what happens when I connect these two. My new line here after the dilation would be parallel to my old one, but I would have a different y-intercept because this would land at a different place on the y-axis. If I just draw out, like, let's say an x and y-axis like this, for both of these, you could see for this one, the line doesn't change, but for this one, we have parallel lines, but the y-intercepts are different. So if this were the more interesting case, then it would be same slope, but different y-intercept. But since the center is on the line, it's going to be the same slope and same y-intercept. So next, we're moving on to part 2. There's 7 questions here, and each question is worth 2 credits. Question 25, on the set of axes below, triangle Dan is congruent to triangle MIK. Describe a sequence of rigid motions that maps triangle Dan onto triangle MIK. Okay, so for this one here, I want to make sure that we're very careful to know where we're starting. We're mapping triangle Dan onto triangle MIK. So just make sure that you start on this triangle here. Now, what I like to do is identify which points are corresponding. So notice that the letter D shows up first and the letter M shows up first. So we want to map this point here, D, to point M. So what I'm noticing here is that this triangle flips. You could see how on the quadrant over here in quadrant 2, the triangle is facing this way. and the corner is pointing in this direction over here. But for this triangle, that point is facing the opposite direction. So we could start by reflecting over the y-axis. Let's see what that does. So to reflect over the y-axis, we're going to count over to the y-axis. We're going 1, 2, 3, 4, 5, 6. So now I'm going to go 1, 2, 3, 4, 5, 6. So that puts us over here. And notice that we're exactly in line with point M. So now we'd have to see, okay, we're going to reflect over the y-axis, and then we're going to go down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I suspect that our sequence of rigid motions is reflect over the y-axis and translate down 11 units. But before I put that down in the writing section, I want to check another pair of points. So A corresponds to I. The letters have to be in corresponding order. So A is over here and I is over here. So let's see if that still works. Reflect over the y-axis, so I go over to the y-axis. So I go one space, so then I have to go one space over like this. And then let's see if we go down 11, if that gets us here. So we go down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So reflect over the y-axis and translate down 11 units will work. Question 26, in parallelogram LEAD below, C is on DE and S is on DA such that SC is perpendicular to DE. If the measure of angle LED is 21 degrees, determine and state the measure of angle CSA. So for this question, what I would do first is just label the information they gave us, okay, or transfer that information to the diagram. So SC is perpendicular to DE means that we have two right angles here. We're also told that the measure of angle LED is 21 degrees. So LED, this angle over here, is 21 degrees. And our goal is to determine and state the measure of angle CSA. So that's this angle over here. I'll just put an X. So here we might get stuck, but just remember, in the beginning, they told us that we're working with a parallelogram. And in a parallelogram, the opposite sides are parallel. So anytime I'm dealing with a parallelogram like this, I always look for alternate interior angles. And to find the alternate interior angles, I look for that classic Z shape like this. And that tells me that if this angle over here is 21 degrees, then this angle here at the bottom is also 21 degrees. And now I have enough information to solve for X. Now, I could get X a few different ways, but the way that jumps out first is the exterior angles theorem. So anytime you have a triangle, let's say like this, and you know this angle here is, let's say, just A and then B, the measure of the angle outside we could find by adding these two angles. So you see how X, I could just add 21 degrees plus this is a 90 degree angle, and that's going to tell me the value of X. Okay, so here I would say, all right, X is equal to 21 plus 90. So here I just have to add to find X, and I would get 111. So now the measure of angle CSA, I'm going to write it in degrees, is 111 degrees. Now, let's say you forgot the exterior angles theorem. There is another way you could do this. You could add these two, and you could say, all right, 180 minus 111 like this. And if you subtract here, so we work this out, we're going to have, this is going to work out to 69 degrees that are left. And then here, I just have to do 180 minus 69 like this. And this would also give me the same exact answer. But the exterior angles theorem is a direct shot. Okay, we don't have to do this two-step process here using the idea that there's 180 degrees inside a triangle and 180 degrees on a straight line. So I prefer to use this theorem here, but either way, we're getting 111 degrees. Question 27, a section of tree trunk from a white pine tree can be modeled by a cylinder. The diameter of the trunk is 1.5 feet, and the height of this section is 8 feet. If white pine weighs 25 pounds per cubic foot, determine and state the weight of this section of the white pine tree to the nearest pound. So for this question, we want to find the weight of this section of the pine tree to the nearest pound. But what we're dealing with is a trunk that is in the shape of a cylinder. So if you go to the reference page says that the volume of a cylinder is capital B times H, where B is the area of the base. Okay, so the area of the base. But let's think about what a cylinder is. So a cylinder, let me just make this nice, is made up of, we have a circle, and then we basically have a stack of circles, and all of the circles have the same dimension, okay, same radius all the way from top to bottom. So this could model the trunk of the white pine tree. Now, they told us the diameter, so the diameter of the trunk is 1.5 feet. So that means the distance going all the way across is 1.5 feet. And they told us the height is 8 feet. Okay, so the height is 8 feet, and that's going this way. I didn't draw this to scale, but that's what's going on here in this question. So what we have to know, though, is the area of the base, if the base is a circle, would be pi r squared. So the full formula would be volume equals pi r squared times height. So here we have to be very careful, though. They gave us the diameter. So if the diameter is 1.5 feet, the radius would be half of this. So I just take 1.5 and divide by 2. Now, if you divide 1.5 by 2, you get 0.75. So the radius is 0.75 feet. So I would start this by just finding the volume. So I do volume equals pi times 0.75, and we have feet inside here being squared, and then the height here is equal to 8 feet. Okay, I should also define here the height is equal to 8 feet. So that's what's getting substituted into the formula. Now, just know, for the regions, you do not have to write units for the free response to get full credit. And if you do write the units, but you write them wrong, you lose points. But just for instructional purposes, I'm going to write the units throughout so you can see how the units cancel when we actually want to find the weight. Okay, so now let's type this in. We have pi, we press second, and then this button over here, the exponent button, and then we have inside the parentheses 0.75, close parentheses, and then squared, and then 8 feet we're going to multiply by, so times 8. And we get this value here, but now let's just think back to this part of the question here. They said that the white pine weighs 25 pounds per cubic foot, and the volume we just found is in terms of cubic feet. So I'm just going to multiply this by 25, but then I'll explain why we're multiplying 25 back, on the test paper. So I'm just going to write this out. Our volume worked out to, we had 14.13716694, and the units are cubic feet. Now, they did tell us to round to the nearest pound, but whatever you do, please make sure you round at the very, very, very end. If you round all of your work to the nearest whole number at every step, it's going to throw your final answer off by a little bit. So just make sure you do that at the very end. So now for the weight, what I'm thinking about is the density formula. Okay, so density is equal to mass over volume. So if I cross multiply here, I could say that mass is equal to density times volume. And that's what I'm going to use here to actually work this out. Now, one thing we're going to do here, though, is we're going to see how the units cancel. So they told us earlier that the density is 25 pounds per cubic foot. Okay, so the density is 25 pounds per cubic foot. Okay, and cubic feet is feet to the third power. So when I want to find the mass here, even though they're telling us to find the weight, okay, so I'll just say the weight though, so we're actually working this out the way, they're asking us. The weight here of the tree trunk is going to be the density times the volume. So I'm doing 25 pounds per cubic feet like this, and then I'm multiplying that by 14 point, that long decimal here, 137,166, and then 94, and then cubic feet at the end. But notice we have cubic feet over cubic feet, which will cancel out. And when we multiply these numbers together, we round up with 353.429 and so on. But to the nearest whole number, we look to the right of the ones place is a 4, and we're going to round down to 353. Okay, so we're going to say the weight to the nearest integer is equal to 353, and we have pounds here. Okay, so this would be our final answer. Now, one extra nerdy detail before we move on. This is not part of the Geometry Regents, but on the Geometry Regents for a question like this, sometimes they'll use the phrase weight and mass interchangeably, but just know mass and weight are not the same thing. This is something that you explore more in physics, but I would, hate to tell you, oh, you could just switch mass and weight. Technically, you can't, but you'll learn more about that in physics. But for the sake of the Regents, you can just say your answer is 353 pounds. Question 28, in triangle ADC below, points B and F are on AC and AD respectively such that AB equals 40, BC equals 30, and BF is drawn. If AF equals 64, determine and state the length of FD that would prove BF is parallel to CD. So for this question, the first thing I would do is transfer the rest of this information over to the picture. So we have AF equals 64, and our goal is to determine and state the length of FD. So FD, I'm going to put an X over here, and we want to know what value of X or what measure for FD would make BF parallel to CD. So here, we're not allowed to assume that these are parallel. We have to find the value of X that would make them parallel. But the good news is we only have to determine and state. We don't actually have to write a sentence. But I'll say something at the end of what you would say if you had to explain your reasoning as well. So here we could use the converse of the side splitter theorem. That's where my head goes, is the side splitter theorem. And the way the side splitter theorem works is when we have a triangle, let's say like this, and a parallel line comes through the triangle. So when I say a parallel line, I just mean a line that is parallel to one of the sides of the triangle. And let's say it cuts the original triangle over in this location. Well, what happens is the triangle is cut proportionally. Okay, so what that means is these two sides over here, AB and AC, the ones that are being cut by the parallel line, are being cut proportionally. And I could say something like AD over BD is equal to AE over EC. Okay, so that's the idea for the side splitter theorem. And that's the idea we're going to use for this question. So here I'm going to say that 40 over 30, this ratio has to be equal to 64 over X. Okay, and then from here, all I have to do is just cross multiply and solve for X. So I have 40X equals, so I'll just work this out. I'm going to do 64 times 30. So 64 times 30, I'll put here. And then I'm going to divide both sides by 40 eventually. So I'll just do that now. We divide both sides by 40, and we're going to get X is 48. So now I'll just show the work. 64 times 30 is 1,920. And now we just divide both sides by 40. And this is going to tell us here that X is equal to 48. Now, if I had to write a sentence here explaining why this works, I would say that BF is parallel to CD when the two sides of the triangle are cut proportionally. Okay, so you could say here, if X is equal to 48, then BF cuts sides AC and AD proportionally, which makes BF parallel to CD. But they didn't tell us to write a sentence, so I wouldn't risk writing a sentence and you say one wrong thing, because then you're opening up the graders to start subtracting points. Now, one thing I want to point out before we move on, the most common mistake with this type of question, if the 40 and 30 were over here, but let's say the 64 and the X were over here, then we cannot set this proportion up like this. The side splitter theorem only applies to the sides being cut. So notice here, the sides being cut are AC and AD, and the numbers and the variables are on those sides that are actually being cut. If 64 and X were on the parallel lines, then we cannot apply this proportion. That's one of the most common mistakes with the side splitter theorem, but what we have here is fine. We have 48, X equals 48 is valid. Now, if we want to play it really safe here, we could also just say, what is the length of FD? I would say that FD is equal to 48 like this, but we labeled FD with an X, so X equals 48 is more than enough. So this would be our answer. Question 29, in triangle CLM below, the measure of angle C equals 33 degrees, CL equals 8, and CM equals 15. Determine and state to the nearest tenth the area of triangle CLM. So for this question, I think of this formula. So the area of a triangle using trig. And I use this formula when I have, let's say, a triangle like this, triangle ABC, and then we label the angles with capital letters and the sides with lowercase letters. So if angle B is over here, then lowercase b would represent the length of this side. Okay, so this is just a common way to label. But to find the area, I could use this formula, 1/2 AB sine capital C. So the way I like to think of this formula, though, that I think helps with all of these questions is instead of saying 1/2 AB sine C, what I do is I say, okay, the two sides here and angle C is the angle between those two sides. So a nicer way to read this formula so that you could do this no matter what the name of the triangle is. Because notice, this is triangle CLM, not triangle ABC. I say 1/2, so the area equals, let me just give a lot of space. The area of a triangle using this formula, I would say 1/2 times side 1, and then times side 2, and then times sine of the angle between. Okay, so this is just another way I like to think of this formula. It's 1/2, and I multiply side 1 and side 2, and then sine of the angle between those two sides. Notice that the 33-degree angle over here is between these two sides. Okay, so over here, we have side that's 8 units long, a side that's 15 units long, and the angle between them is 33 degrees. So when I do this formula, I would just say, all right, the area of triangle CLM is equal to 1/2. I multiply side 1 and side 2, so that's 8 times 15, and then I multiply by sine of the angle between them is 33 degrees. Now for this part, please make sure you are in degree mode. So remember, if you're not in degree mode, you press mode and go from radians here over to degrees and press enter, and press second mode to go back to the main screen. So 1/2, I could say 0.5 times 8, and then times 15. And then we're multiplying that by sine of 33 degrees. We press enter, and this will give us our area. So we're finding the area to the nearest tenth. In the tenths place is a 6. To the right is a 7. So we're going to round this up and say the area of triangle CLM is equal to 32.7. Okay, so this would be our final answer. Question 30, in the diagram of triangle ABC below, use a compass and straight edge to construct the angle bisector of angle ABC. So for this question, first, it's very important that we actually bisect the correct angle. So if they're telling us to bisect angle ABC, that tells us that we are bisecting this angle down here. So we're going from A to B to C. So this is the angle that we're going to cut in half. So what we do is we take the compass over here, we place the point at the vertex B, we open it up, but don't open it so far that when you swing the arc, that it's going to miss the triangle completely. You want to make sure you open it in such a way so that when you swing the arc, that's going to hit two sides of the triangle. So we hit one side over here, and we hit the other side over here. So now we can take the compass and we can move it over to the point of intersection here. Now, when we swing the next arc here, we should open the compass a little bit because we want it to go more than halfway so that we have another point of intersection to make our angle bisectors. So I open it up enough so that, once again, I don't open it all the way so that it flies off the page, but I open it enough so that we could get another point of intersection. So now I swing the arc from this point that we just made, and I go like this. And now at this step, I do not change the length of the compass. I keep it the same, and I move the compass over here to this point, and I move it, swing the arc. So there's our second point. So now all we have to do is just connect point B over to this point of intersection here, and this is our angle bisector of angle ABC. If RP equals 12 and GA equals 24, explain why gram is a rectangle. So for this question here, the first thing I would do is just draw this out. So I'm going to draw out a rectangle, and the rectangle, I'm going to name it rectangle gram. Okay, so we have GRAM. And what they told us is the diagonals intersect at P. So I'm going to draw in the diagonals, and I'm going to label the point of intersection as point P. So that's going to go over here. And they told us that RP is equal to 12. And they told us that GA, this entire segment here, so from here to here, this entire piece is 24 units long. So this piece is 24 units long. You have to explain why gram is a rectangle. So what I'm thinking with this question is I want to show the diagonals are congruent. Okay, so a parallelogram, so I'm going to write here a parallelogram with congruent diagonals is a rectangle. Okay, that's the first thought that comes to mind. A parallelogram with congruent diagonals is a rectangle. And it's very important that they started us off by saying that this is a parallelogram, because this reasoning only works if we're going from parallelogram to rectangle. Now, some other important idea is the diagonals of a parallelogram bisect each other. So that would tell us that MP, this segment over here, is also 12 units long. So I would say, just to explain, I would say the diagonals of a parallelogram bisect each other. So the diagonals of a parallelogram, and you could abbreviate parallelogram by drawing one and writing P inside. So the diagonals of a parallelogram bisect each other. And now the conclusion that we could draw from this is then we could say that MP, so I could say therefore MP equals 12. So this tells us the entire diagonal MR. So MR is equal to 24. But now the next idea I want to get down is that the diagonals are congruent. So what we could say next is we could say that MR is congruent to GA, or yeah, I could say GA or AG. So GA. And the reasoning, I'm going to say because they are equal in measure. Okay, because they are equal in measure. So once we get this statement down here, we showed the diagonals are congruent. Now we could write that concluding sentence. So now I will say the final sentence here. We could say gram is a rectangle because it is a parallelogram with congruent diagonals. Because it is a parallelogram with congruent diagonals. Okay, so this gets all the ideas down. Okay, this is, very important, I think, to just be as thorough as possible. So we're saying how we know MP is equal to 12. And then that allows us to show diagonals are congruent, and then we write our conclusion. So now we're moving on to part 3. There's 3 questions here, and each question is worth 4 credits. Question 32, as modeled below, Maria wants to determine the height of the building across the street from her position M. The angle of elevation from M to the top of the building T is 36 degrees. From M, the angle of depression to the base of the building B is 18 degrees, and the buildings are 80 feet apart. Determine and state to the nearest foot the height of the building TB across the street from Maria. So for this question, we're going to use trig. And what we have to do is we have to look at 2 separate right triangles. So we have a right triangle over here, the one that I am highlighting in green. And we have another right triangle just underneath. And I'll highlight the next one here in purple. Okay, so we have this one over here. So this one, I'm just going to put in a different color, is the other one that we're going to work with. So what we're going to do is we're going to solve for the measure of, I'm going to call this piece over here X, and I'm going to call the other piece here from H to B, I'm going to call that Y. And what we know is the distance between the buildings is 80 feet. So I could label this segment over here with an 80. So now I'm going to use 2 separate angles. We have this angle here, and we have this angle over here. And if I focus on the green triangle first, we have a right angle over here. 36 degrees is here, and X is the side opposite. Okay, this side here is opposite of the 36 degree angle, and the 80 would represent the side that is adjacent. Okay, so this one here is adjacent. And then in the purple triangle, we have 18 degrees over here. The side labeled Y is opposite. Okay, so this one here is opposite. So for both of these, what I'm hearing is opposite adjacent. So if you say the phrase to yourself, so katoa, we are going to go with tangent here. Okay, we're going to go with tangent. And we're using tangent because tangent of an angle theta inside a right triangle, where theta is one of the positive acute angles, is equal to the ratio of the side opposite of the angle over the side adjacent to the angle. Okay, so that's what I'm going to use here for this question. So I'll do the green stuff first. So we're going to have tangent of 36 degrees equals, and opposite is X over adjacent is 80. Okay, so this will tell us the value of X. All I have to do is just cross multiply, and X is equal to 80 times tangent of 36 degrees. When you multiply a number by a trig function, you can just write the number in front as a coefficient. And now I'll do the same thing for the triangle in purple. So now we're going to have tangent of, this time we're using the 18 degree angle, and this is going to be equal to opposite, we label that with Y, over adjacent. That side is still 80 units long here, or 80 feet long if we want to use the actual units. And now we just cross multiply. So Y is equal to 80 times tangent of 18 degrees. So now notice here, our goal is to find the length of TB. And I can point out here that TB is equal to X plus Y. So I'm going to say TB is equal to X is 80 times tangent of 36 degrees plus y is 80 times tangent of 18 degrees. And now we just type this in. So we could do this all in one shot. We could write 80 times tangent of 36 degrees. Make sure you close the parentheses. Plus 80 times tangent of 18 degrees. And we press enter. We're rounding to the nearest foot. So we're going to say 84 feet. So we could just write this out. We have TB is equal to, and we have 84.11, and then we have 697794. But they said for the height of the building to round to the nearest foot. So I'm going to go to the ones place is a 4. To the right is a 1, so we round down, and we would say 84 feet. This is the height of the building. Question 33, an artist uses clay to make solid pyramids with a square base whose sides measure 12 centimeters as modeled below. The height of each pyramid is 8 centimeters, and the density of the clay is 1.25 grams per cubic centimeter. If the artist has 15 kilograms of clay, determine and state the maximum number of pyramids that can be made. Okay, for this question, we have a few things going on. But first, we should find the volume of this pyramid. So the volume of a pyramid from the reference page is 1/3 capital B times H, where capital B is the area of the base. And in this case here, we have a square base. Okay, so see over here, we have a square base, and the area of a square is just side times side. Okay, so that's where my thinking goes first, is I just think, okay, if I have a square and the sides are S units long, the area is equal to S squared. So what I'm going to do here, I'm going to find the volume. I'm going to say volume equals 1/3 capital B. I'm finding the area of the base. Let me just make this a little neater. I'm doing 12 centimeters times 12 centimeters. And then for the height, they told us the height of the pyramid is 8 centimeters. So that would be this space here going down. So I'm just going to write over here, the height is 8 centimeters, and we still have to multiply by the height, 8 centimeters. So now we work this out. We have 1/3 times 12 times 12, and then times 8. Okay, and this gives us the volume of the pyramid in cubic centimeters. So now we could say the volume is equal to 384 cubic centimeters. I'm doing centimeters times centimeters times centimeters is centimeters to the 3rd power. Now, once again, you do not have to write units to get full credit for a question like this, but I like to write the units here so we could see how everything interacts. So now, the next thing we know is the density of the clay is 1.25 grams per cubic centimeter. And remember from before, density is equal to mass over volume. So if I cross multiply, I could say the mass is equal to density times volume. So I'm going to find the mass of 1. And from here, what I could say is, all right, the mass of 1 is equal to 384 cubic centimeters times the density. And they told us the density is equal to, I'll write it over here, the density is 1.25 grams. So I'm going to make that a little neater. So grams per cubic centimeter. Okay, so I'm multiplying by 1.25, and we have grams per cubic centimeter. But the only problem here is when we work this out, notice the units that we're left with. We're left with grams. And what we have to account for next is if the artist has 15 kilograms of clay. Okay, so this part here is very sneaky. It's very important, though, that we know that 1 kilogram is equal to 1,000 grams. So once we have this information, we're going to get the mass in grams, but we want the mass in kilograms. So what I would do with this information is I would multiply this by, we have 1 kilogram for every 1,000 grams. Okay, so this part here is very important that we account for the mass in kilograms. All right, so we're just dividing this value here by 1,000. So now we could do 384 and multiply that by 1.25. And then we're going to multiply that by 1 over 1,000. Or I could just say divide by 1,000. Okay, so we divide that by 1,000 and we get 0.48 kilograms. But now they're telling us the artist has this many kilograms of clay to work with. So how many pyramids can be made? So we just have to take the 15 now and divide by the amount of clay it takes to make 1 pyramid. So we're taking the 15 kilograms and dividing by 0.48 kilograms to see how many pyramids can be made. So now let's write this out here. The mass, and this is the mass of, I'll just point out over here, of 1 pyramid. Okay, the mass of 1 pyramid is equal to, we had 0.48 kilograms. Okay, and we wound up with kilograms once again because we converted units over here. Grams over grams cancels, and we're left with kilograms. But now that we have the mass of one pyramid, and I'm going to point out this is also true for the volume that we found over here. Like this is the volume of one. So this is all for one pyramid. We could take 15 kilograms and divide it by 0.48 kilograms. Okay, so this I divide because once again, there's 15 kilograms of clay for the artist to work with, but each pyramid requires 0.48 kilograms. So that's why we divide like this, and we get 31.25. And they're asking us to state the maximum number of pyramids that can be made. So even if this wound up as 31.8, we would still have to say 31 pyramids because you need to pass, we would have to have 32 here to make it to the 32nd pyramid. This is not rounding in the traditional sense where we say 4 or lower or 5 or higher. This is real world scenario. So we would say 31 pyramids because that's the biggest integer we have if we, ignore what's after the decimal here. So 31 pyramids, and this is going to be our solution. Question 34, given triangle ABC, AB is congruent to AC, DE is perpendicular to BC, and HF is perpendicular to BC. And we have to prove that DE over BE is equal to HF over CF. So for a question like this, what I like to do is I like to work backwards. I think about what we're trying to prove, what's our end goal, and then I come up with a strategy based on that. Our goal is to prove that we have sides in proportion in these two triangles over here. Okay, so if we need to prove that we have proportional sides, we have to think about where that's going to come from. Proportional sides would only exist if we have similar triangles. Okay, so what we want to prove here, we want to prove that triangle DEB is similar to triangle HFC. Okay, we need to prove these two triangles are similar. And how do we prove two triangles are similar? We have to show that we have a pair of congruent angles. So now I can start transferring the givens over to the diagram. So I look here and they told us DE is perpendicular to BC. That allows us to say that we have right angles over here. They also told us HF is perpendicular to BC, so we have right angles over here. So if I focus on the two triangles I'm trying to show are similar, so far I have one pair of congruent angles because they both have a right angle. And then next, I might get stuck on finding the last pair of congruent angles, but then I use this phrase. I say, what information did they give me that I didn't use yet? And I didn't use this yet. AB is congruent to AC tells us that the angles opposite of those congruent sides are congruent. So that could tell us then that angle B is congruent to angle C. So there's the angle, which allows us to say the triangles are similar, which allows us to say the sides are in proportion. So now I could start thinking about my statements and reasons. Now, something that's very important when you are writing out your statements and reasons, even though it's very tiring, it's very important that you write the givens as your first statement. If you do not include the givens, then you don't get full credit. So now that we have the givens established, we can move on to the strategy we have here. We want to establish angle. So what we need to say is we have two pairs of congruent angles. So let's start off here saying angle B is congruent to angle C. Well, how do we know this is true? Well, for our reason, we could say in a triangle, angles opposite congruent sides are congruent. So when we're writing our statements and reasons, we are allowed to abbreviate like this. So triangle, I just draw a triangle, and for congruent, I just write the symbol. Now, once again, just to recap, we know this is true because they told us AB is congruent to AC, and notice that angle B is opposite of side AC, and angle C is opposite of side AB. So this, we're just using the, this is coming from the isosceles triangle theorem, but I like writing it this way because we don't actually have to say this triangle is isosceles when we write it out like this. So then next, I want to establish the next pair of angles are congruent. So far we established we have one pair of congruent angles. So now we have to establish the other angles are congruent. And the other ones I'm talking about are, we have angle DEB. So angle DEB is congruent to angle HFC. And the reason why this is true, we could say perpendicular lines form congruent right angles. There was an old way of writing this where you would write this in two statements and reasons. First, you would say, hey, DEB, angle DEB and angle HFC are right angles. Perpendicular lines form right angles. And then a moment later say, hey, they're congruent. All right angles are congruent. But this is an acceptable way to say this in just one statement and reason. And the less you have to write, the better. So now that we've established that we have two pairs of congruent angles, we can now say the triangles are similar. So now let's write, we have triangle DEB is similar to triangle HFC. And how do we know this is true? This is true by angle, angle. And now that we've established that the triangles are similar, we could say that their corresponding sides are in proportion. So we have DE over BE. So this ratio here, see we have like the vertical side to the horizontal side is an equal ratio to the ratio of the vertical side to the horizontal side in the other triangle. So now let's just write the rest out. We have HF over CF. And for our reason, we're going to say corresponding sides of similar triangles are in proportion. So now we're moving on to part 4, the final question, and this question is worth 6 credits. Question 35, triangle ABC has vertices whose coordinates are A, -3, -1, B, -5, 2, and C, -1, 8. And first we have to state the coordinates of point D such that quadrilateral ABCD is a parallelogram. The use of the set of axes on the next page is optional. And then after that, we have to prove that ABCD is a parallelogram. When they give you the set of axes, I highly recommend that you use them because it really helps you come up with a good strategy for the proof part of the question. So I'm going to start by plotting A is at -3, -1. So that's 1, 2, 3 to the left, and then down 1. So here's A. B is at -5, 2. So I go to the left 5 and up 2. And then point C is over 1 to the left, and then up 8 over here. So here's points A, B, C, but first we have to find where is point D, and we want to find point D so that it makes ABCD a parallelogram. Now, the big idea that we're going to use for this question is that in a parallelogram, opposite sides are parallel, okay? Opposite sides are parallel. And if opposite sides are parallel, I'll say also opposite sides have the same slope. Have the same slope. That is the big idea that we are going to use here. I think this is the easiest way to find the missing point is to use the slopes. So now what I'm going to do is I'm going to find the slope from point A to point B. The slope from point A to point B, I could say is the slope of AB like this. So lowercase m with a subscript AB with the line over it like this. So the slope I could just find by doing rise over run. I have to go down 1, 2, 3, and I have to go over 2. Okay, so the slope is -3 over 2. It's not +3 over 2 because this segment here is dropping. If I were to connect these, notice this is a dropping line segment. It's not going up, so the slope should be negative. Well, if the slope is -3 over 2, then I could do the same thing over here to find where point D is. So this would be down 1, 2, 3, and then over 2. I go down 3 over 2, and this tells us point D would have to be over here in this location here. Okay, point D would have to be at over 1, up 1, 2, 3, 4, 5. So D is going to be at 1, 5. And the question is also telling us to prove ABCD is a parallelogram. So I'm going to go ahead and find the slopes of all the sides. Now, one little detail I want to point out. This is a common mistake. I see students go through this question and they find point D to be somewhere over here because they say, all right, I could just match the slope from here to here and then go in this direction. The problem with that is the letters have to be in correct order. It has to be A, B, C, D when we go clockwise like this. If we put point D somewhere over here to make the parallelogram go this way, the problem with that is it would be parallelogram ABDC, not ABCD. So it's very important that the letters stay in order. When you go clockwise or counterclockwise, it should write out the letters of your shape. Okay, so you can't just like switch letters back and forth. It's a very small detail, but it does throw people off. So we have over here the slope of CD. So let me just write this out here in matching color here. The slope of CD, I showed the work on the graph here by going down 3 over 2 like this, is -3 halves. But then I'm going to find the slope of the other two sides. So the slope of BC, I would count the rise over run. I'm going up 1, 2, 3, 4, 5, 6. And I'm going over 1, 2, 3, 4. So this is up 6 over 4. And this I could reduce if I divide top and bottom by 2. The slope of BC is equal to 3/2. And now finally, I'll find the slope of the last side, AD. And the slope of this side, I go up 1, 2, 3, 4, 5, 6, and over 1, 2, 3, 4. So this slope is also 6 over 4, which reduces to 3/2 again. Okay, so here I have the slope of all four sides now. And notice these slopes are equal, which tells us if we have equal slopes, the line segments are parallel. And then we have equal slopes here. So these line segments are parallel. So both pairs of opposite sides are parallel, which makes ABCD a parallelogram. So I just transferred some of the information from the other page back to the first page. And over here, we have point D is at 1, 5. But now how do we actually write out the proof? For this type of proof, I like to use a flowchart. So first I would comment and say, hey, these are equal. And since the slopes are equal, this allows us to say that AB is parallel to CD. And then over here, I could say the same thing. I could say, hey, these are equal. And what does that tell us? It tells us that BC is parallel to AD. But now what do these two statements here tell us together? Well, they tell us that ABCD is a parallelogram. And how do we know ABCD is a parallelogram? Because both pairs of opposite sides are parallel. Okay, so ABCD is a parallelogram because both pairs of opposite sides are parallel. So now for the next part here, we have to state the coordinates of point E, the midpoint of BC. So first we could use the formula, and then I'll verify that what we found is reasonable. So this is the formula for the midpoint of any line segment. And what we could do is we could just plug the points in for B and C into the formula. So B we could call our x1, y1, and then C will be our x2, y2. So then point E, this is going to allow us to say that point E is going to be located at, I do x1 plus x2 divided by 2, comma, and then I do y1 plus y2 divided by 2. So here this tells us that E is located at -6 divided by 2 is -3, and 10 divided by 2 is 5. So -3, 5. But now let's see if -3, 5 is reasonable. If we go over to our graph from before and we plot the point -1, 2, 3, and then up 1, 2, 3, 4, 5, this is a very reasonable location for point E. This is very visually convincing that E is the midpoint of segment BC. So -3, 5 is definitely good. So now for the last part of this question, we want to prove that triangle ABE is an isosceles triangle, and the use of the set of axes below is optional. So let's look at what we have here on the graph. If we look at triangle ABE, if we're going to show this triangle as isosceles, we have to be able to show that two of the sides are equal in measure. We can't just say, hey, this triangle is isosceles because it looks isosceles. Two sides look to be about the same. We have to be precise, so we're going to use the distance formula. So let's write out the distance formula. We have distance equals, and then we have a square root. And inside the square root, we have parentheses x2 minus x1 squared. And then plus y2 minus y1 squared. So if I find, let's say, the length of AB, what I'm going to do is I'm going to write out a square root. And then I'm going to take the difference of the x values and square it, okay? And I'm going to write the -5 first. We have -5 minus -3, and this quantity is being squared. And then plus, now we do the difference of the y values. So we would do here 2 minus -1. If I start off by writing -5 first, then I should start off by writing the 2 here. So I would start with this y value. So we have 2 minus and then -1 squared. So then from here, we just simplify. So this would work out to, let's see, we have -5 minus -3 is -2, and -2 squared gives us 4. And then we have plus, this would give us 2 plus 1 on the inside, so we have 3 squared is 9, and this tells us then that AB is equal to square root of 13. But let's say you forget the distance formula. Well, another way you could find the length of a segment is you could just use the Pythagorean theorem on the graph. So far we have AB is equal to square root of 13. So when we go to the graph here, we should be able to show that BE is also square root of 13. So if we zoom in over here, what I'm going to do is, if I want to find the length of BE without the distance formula, I'm going to use rise over run and then the Pythagorean theorem. So to get from B to E, we have to go up 1, 2, 3. So we're going up 3 and then over 2. So if I draw this off to the side here, we have a right triangle where this side here is 3 units long. This side is 2 units long. And then just imagine we have over here B and E like this. So when we want to find the length of BE, we could just use the Pythagorean theorem. So I'll write this over here. I'll say that BE squared is equal to, we have 3 squared plus 2 squared. And this gives us BE squared is equal to 9 plus 4 is 13. We take the square root of both sides, and notice this gives us BE is equal to square root 13. So now some commentary, I could say that these two sides here are equal, which then tells us that segment AB is congruent to segment BE. But now this establishes what we need to prove triangle ABE is isosceles, because we have a triangle with two congruent sides.